So welcome back. Today we're going to take on a relatively ambitious project. We're going to implement TCP. For those of you who aren't aware, TCP is basically one of the fundamental protocols of the internet. It's the way that basically enables two different hosts on the internet to talk to one another in a reliable way so that you can send data in such a way that you're guaranteed to not lose anything that you send and that the receiver receives things in the same order you sent them. The internet does not generally guarantee this. And so TCP is a protocol that basically sequences data across the network and makes sure to do things like retransmissions if packets are lost. There have been a couple of questions in chat just before we started about like how much of TCP are we trying to implement. The goal is to implement basically something that can talk to a real server. Now, how we define real server, we'll get to in a while, but the idea is that we want the ability to talk to a real host on the internet. So talk to some TCP implementation that is not our own. This means that we're not going to implement any of the sort of advanced extensions to TCP or any of the sort of advanced congestion control algorithms, for example. We're just going to implement sort of the basic, probably neutrino. And so what we're going to be working for is RFC 793, if I remember correctly. This one. Or I guess actually I want this one. So this one is the RFC for TCP, the Transmission Control Protocol. As you saw from Twitter, I think I posted out here. There are a couple of other RFCs that are handy to follow. In particular, why is this being weird? No. In particular, there's sort of this tutorial. I'm not going to read through it. This is just good background for people who want to understand how TCP works. I'll give a very brief overview, sort of drawing some figures and such, but I'm sort of assuming that you roughly know what TCP is. I don't expect you to know the protocol by heart or what all the headers are, but that you sort of know what it's doing. So I will not go through this particular RFC. This document we're probably going to refer to a lot. So RFC 7414 is basically a list of other RFCs that you probably need to implement. We're not going to implement anywhere near all of them. In particular, we're going to focus on the things that are listed as core functionality, which is basically things that you must implement to be a TCP host on the internet. And that is basically 793, which is the core TCP protocol. 1122 defines a couple of other things like additional extensions you need to support, and from memory, some like initial values you need to set for different bits. We're going to ignore this because we're not going to support IPv6. This, I think, is basically possible to ignore. And this one is basic congestion control. So we need to set up like basically Reno, which is pretty much slow start would be my guess. And there's like some stuff on retransmission timers and segment sizes. So these things down here will be relatively short extensions to the core thing which we're going to do in 793. So my guess is that for this particular stream, our hope is to get somewhere decently far with 793. And whether we actually get there or not, we'll have to see. But the hope is that we get 793 and then we can do all the extensions maybe in the next stream. And then hopefully at that point we can talk to other hosts. So hopefully that gives you some rough idea. There's also RFC 2398. So 2398 gives a bunch of tools for testing TCP implementations. My hope is that we'll get to try some of these after a while, but that's sufficiently far down the line that I'm just going to close it for now because it's not terribly important. This RFC 2525 is just a really handy way to debug TCP implementations because it gives a number of sort of known problems with past implementations and what the problem probably is if you experience one of these particular issues. So we might end up referring back to this. So I'll keep it open, although the core thing is going to be 793. Before we dive into that, there are a couple of small things I want to talk about. So first, there's the live coding voting site. So this is how we ended up doing implement TCP this time. There are a bunch of other proposals too for upcoming streams. So here, if you go to the site, you just put in a unique username and then you just drag these ideas according to which one you would rather like to see me do. And it basically runs a it runs now I can't even remember what it's called. Rank choice voting to determine which one is the next upcoming stream, and then also to figure out things like runner-ups so that we can keep running basically elections, even if people only vote once. Why is this not following the chat? Okay, so that's the live coding stream voting site. The other thing I want to mention is the last sequence of streams we did was porting FlameGraph to Rust. And so we ended up with this tool called Inferno. And Inferno has actually been doing really well. There have been a bunch of people contributing. We now have full color support. And so if you look here, we already have 9 different people contributing. So we have Jason has been doing a lot of work for doing things like supporting additional features like name attributes and stuff. BC Myers has been doing some work on adding, sort of cleaning up the interfaces, some performance hacking. Jordy has been doing a bunch of work on coloring. And so this has just been a really cool project, and there are still lots of open issues. So if you want to try to contribute to something that is sort of simpler than what we're going to be working on today, then Inferno is a really good place to start. And all the past streams are, of course, up on YouTube, as always. All right, so let's get started with TCP. In the tweets where I announced this, I announced we were going to use this crate. So PNet is basically a way to do low-level networking. Normally, I don't do any research before I do my streams. In this particular case, I knew that there were some weird things we were going to have to run into when we start dealing with low-level networking. In particular, once you want to do things like implement TCP yourself, you run into the issue of the kernel already implements TCP, and you sort of need to steal packets from the kernel. But the kernel needs to know which packets you're going to steal from it. So that you end up in this sort of weird position where the packets sort of go to the kernel and to you, and it's just a little bit of a pain. And so we're actually not going to use libpnet because it uses, as far as I can tell, it uses raw sockets, and raw sockets are nice if you're implementing your own protocols, but not so great if you're implementing TCP because the kernel is still going to the kernel is still going to run its own TCP stack, and that might interfere with the things that we're trying to do. So instead, we're going to use this Linux feature. Actually, let's put this here. This Linux feature called tuntap. So tuntap are basically user space, so not in the kernel, but in the user space, a way to write what essentially looks like a network to the kernel. And so what you're going to do is you tell the kernel to create a network interface for you. Actually, let me draw this. It's going to be easier. Here. And if you have any questions at any point during this, getting sort of the basics of this is pretty important. So if you feel like there's something you're stuck on, then just give me a shout. What do I want? I want that one. Okay, so in normal applications, what we usually do is we draw the kernel as a thing down here, and then user space sort of on top of the kernel. Wow, this one is not great for writing. Let's do pen. And then you can imagine down here is the big scary internet. And there are going to be a bunch of packets, and they sort of arrive down here at a thing called a NIC, a network interface. Provide the link to that kernel patch. It's not a kernel patch actually. It's just a description of tuntap. So if you search for just tuntap.txt, you should find it. But I can post it to chat as well, I guess. It is... My chat is on a different machine over there, so I can't put anything there. That one. So I don't know if you got that, but let's go back to this. So there's sort of a network interface, and that receives all the packets that come from the network, and the kernel sort of internally has a bunch of data structures that it uses to run things like TCP, and it's going to send responses here. if user space wants to talk over the network, they create a socket by calling into the kernel. The kernel allocates some kernel memory for that socket that represents that TCP connection. And then the user space thing is really just a pointer to the thing in the kernel. And so this is how normal networking works, that if you want to say read or write from a network connection, then you just give this identifier that the kernel gave you. That's normally just a number, like a file descriptor. And you say like, write these bytes to that file descriptor. That goes to the kernel. The kernel then knows how to talk TCP and send stuff back on the interface card. So what's going to happen in our case is that we still have this sort of user space and kernel divide. Like so. And what we're going to do is we're going to have the kernel create what is basically a virtual interface for us. I'm going to draw that here. So this is a ton interface. And it's going to treat that as if it's its own network card. So it's going to treat anything that comes out of this as something that sort of came from the network, right? It's going to treat this as a NIC, as a network interface. However, it basically is going to consider this sort of the wire of that network. So anytime it tries to send on this network interface, that's really just going to appear out of here into the user space program. So the user has like a process running here, and basically any send the kernel does turns into a receive in the user space program. And similarly, anytime the user space program writes something, that's going to sort of go through that and appear to the kernel as though that was a packet that came from the network. So this basically lets us emulate a network inside of user space. So that's what a ton device does. And effectively, what it gives you is, so there's the command IP that lists all the interfaces on your machine. IP, if we create a ton interface, is going to show that there's an additional interface like ton 0 that has like some IP, who knows what it's going to be, and like a bunch of other information. And if we try to send something on this, what's going to happen is that the kernel is going to look up which process owns this tunnel or this ton. And then it's going to take whatever the kernel wrote into this interface, whatever raw bits of a packet it wrote into here, those are going to be redirected into user space. And whatever user space writes back is going to be treated as if it came back onto this network socket. And this allows us to implement TCP pretty nicely, right? Because we on here, all we have to do is just like implement our TCP stack. And if we receive a packet, then what really happened was the kernel sent a packet to this address, and we're just going to interpret it as a TCP packet, and we're going to send responses back to the kernel, and the kernel is going to think it's talking to some host on the internet. Why is this not following chat? It's very unfortunate. Okay, so does that roughly make sense? We're going to get into a lot more detail about how exactly we end up using ton, but does the rough idea make sense? That the ton that we create is basically a user space network. Yeah, that the link posted by Wilkins is basically the same document. Okay. And that means that instead of using the pnet package, we're actually going to use this ton tap crate. So luckily, there's a Rust crate for this. Hello. So luckily, there's a crate for this. And it's pretty straightforward, right? What you do is you have a ton tap interface. Ignore tap for now. And you can create a new one. You can give it a name. Or you give it a name, it can be empty, and then the kernel just generates one for you. You can choose the mode for it, and we're going to ignore mode for now. And that gives you an interface. And once you have an interface, you can call receive to receive a message, and you can call send to send a message, right? Which is sort of what you want. Why is this not following chat? I have to scroll down anytime someone sends a message, which is not ideal. Let's try that instead. Yeah, so all this gives us is a receive and a send, and what these receives and sends are basically IP packets. So anytime the kernel sends an IP packet to us, So anytime the kernel basically sets network traffic our way, the receive is going to give us back the bytes contained in that packet. And similarly, we can send bytes out, and the kernel is going to receive those as an IP packet. What this means, unfortunately, is that we also need to implement the IP protocol, because we need to be able to send packets to the internet. Luckily, the IP protocol is a little bit simpler. It's basically just you name the remote machine. Don't you risk freezing the entire system if you mess something up? Asking because I would like to follow along without my PC crashing every attempt at running the thing. It's unlikely that the entire system is going to freeze. Like the kernel is not, like, you're not going to crash the kernel using a ton interface. However, what you might do if you screw things up is you might set up the routing tables on your host machine so that you can't talk to the internet anymore. Usually all you have to do in that case is like reboot or restart your network interface. I'm hoping that this will not happen to me because then the stream will be cut off. But in theory, at least, we should be fine. But the biggest concern is that your network traffic can no longer be routed. Like imagine that basically if your entire network connection started going over the TON interface, then nothing is going to go to the internet. Every packet you send is just going to go to it's just going to go directly to the process you're writing, which doesn't know how to talk to the internet. It might be better to work in a VM, although, again, I don't think you can really break anything this way, and I don't particularly want to work in a VM. But I agree, you totally could, and it might be better. I just don't want to. But yeah, so this gives us basically the interface we need. There's one thing that's then missing, and that is the RFC for the IP protocol, which is 791. And luckily, the IP protocol is very, very straightforward. I don't need all the description. Basically, when you send an IP protocol message, it looks like this. So there's like a bunch of fields that we basically can ignore. Well, we're going to have to set them, but they mostly have constants. And then there's a source address and a destination address. The source address is going to be the IP address of sort of us, as in who we're pretending to be on the user network that we're creating, and the destination address is going to be the remote host that we're talking to. I don't think we're going to need any options, and then following this header is just going to be the contents of the packet. Do you need to be root? So generally, you need to be root to create these things, but there is a capability, specifically capnet admin, that you can. So this is basically the thing you can tell the kernel to give a particular process or binary. You can say that when this program runs, it's going to have this capability, which means that it's going to be able to do these things without having to be root. So we should not need to be root for this. You do have to be root to grant this capability. Okay, so let's get started, I think, is the way to go. I think step one of this is going to be just making sure that we're able to send and receive packets at all. And so, as before, we're going to go into streams, and we're going to cargo new lib. Actually, is it going to be a lib or a bin? Let's make it a bin for now. Let's start simple. We're going to call it, what are we going to call it? Thanks. What are we going to call this user space TCP thing? It's going to be, it's going to be trust. TCP Rust. All right. And we're, of course, going to depend on the tuntap crate. 0, 1, 2. And source main is going to do an extern crate tuntap. And then I guess what we're going to do here is something like ton tap. This is just to see that we can get anything working. Mode, what's the we specifically want? Ton mode. Don't worry too much about the difference between ton and tap. I mean, I can explain it if you want to, but I don't think it's relevant. Fail to... Actually, now main is allowed to return a result, right? I think that's true. And thunder is pretty funny, actually. Although, oh, you're right. I don't need extern crate. Thanks. I like thunder. Wait, that's a great name. Actually, I agree. Let's switch it to thunder. Well, so the reason trust is nice is because TCP basically, it doesn't actually establish trust, but it does mean that you can trust that what you send is what the other person receives. Actually, let's keep it thrust for now, and then we can figure that out later. I was planning on using stable, although who knows? I don't remember what my default is. My default is beta, so we're on beta. Okay, so we're gonna do. We're gonna create a new interface, and then we are going to do. Buff is going to be a 1500, and I'll explain why soon. Actually, I don't think we need packet info. Yeah, let's do without packet info. No, this is your new, fine, for now. 0U8. Oh, it's the other way around, right? U8 this. And then we're gonna do nic.receive into buff. And we're gonna do read this many, actually, yeah. And then I guess we're gonna X this. How many bytes we read? I guess this is n bytes. And this is gonna be buff n bytes. Let's just like see whether that works at all. Just so we have a place to start. In fact, it almost guaranteed will not. Ooh. Ton tap not found. Oh, it's... Oh, they've done it properly. Nice. Oh yeah, Tsunami was great. It was a good crate name too. Oh, iFace. And what else are we missing? Oh, what's, I guess like this? Oh. Don't need both. And then because we're going to be doing like networking things, we're also going to do sudo set cap, what was it capability called? Capnet admin on target dir release trust. Huh? You don't need a use statement because with uniform paths, any identifier is any identifier to the left of all the colons is considers anything that is in scope and all external crates. Sorry, why can't I do this? Set cap dash h dash r dash what? Help. Man, set cap. Oh, is it like has to be lowercase or something? Cap net admin. What? Apparently not. Equals EIP. What is the equals for? Man cap from text. Oh. Each clause consists of a list of comma separated capability names. An action list consists of legal flags. Okay, what do the flags mean? Sequent flags indicate that the list of capabilities requirements are supposed to be erased. For example, XP means lower every capability effective and inheritable. Oh, we just want to set them for all of them, sure. Equals EIP. Great. And now, I think in theory, we should be able to run this thing. Okay, it did an error. So let's look at what IP addresses we have. Okay, so we now have a ton 0 interface. It doesn't have an address or anything, so we don't actually know how to send anything to it yet. So let's do IP adder set 6801/24 dev ton 0. Oh, add. All right. So this still hasn't received anything, at least as far as we can tell. But now, and then also set link set up dev ton 0. Great. So here it got a packet. I have no idea what packet this is, but this is indeed a packet that it got. One thing so as you notice, this just got a bunch of bits now, right? So clearly it is receiving some stuff. Like when we brought this link up, it received an IP packet of some kind. I don't know what kind of IP packet, maybe a ping packet or something. But it did receive an IP packet. And so that suggests that our basic setup is working. And now you see ton 0 is gone, right? What we're probably going to want, because running this thing is a little annoying, is we're going to want to do something like have this in a script. And that's going to do cargo b release. It's going to do that. Then it's going to do what we did over here. And also what we did up here to set the address. This is basically so that we don't have to run this every time. Ooh. just wait PID? I think it's wait PID. Oh, maybe it's just wait. Yeah, it's just wait. So what the script is doing is it's building, setting the capability, running the binary in the background, keeping the process ID of that around, setting up the network, and then waiting on that process to finish, which in this case is going to read the 52 bytes. As you've observed, though, like this is a little weird in the sense that we don't know what these bits are. So we're going to want some kind of tool that can help us interpret what these are. And we will probably want our program to not just exit too, right? Something like loop. So now if we do run sh, then now it's going to continue. So now the IP, this is still up. And now let's try to do something like ping on interface ton 0. We're going to ping some address on that subnet. So this now received a bunch of more bytes. In fact, you'll notice that it keeps receiving bytes, and these are in this case ping packets, right? And so now we're going to have to interpret these in our program so that we can like parse them as TCP packets, for example. And so what we're going to do is use, there are a bunch of tools you can use here. I'm going to use one called Tshark. So this is a terminal version of Wireshark. And notice that it gets to sort of watch this interface and see what's going on. And specifically, see this the 52 bytes thing was a IPv6 router solicitation. That sounds like something we should ignore. And then all of the other ones are requests, and of course there are no responses because our program doesn't do anything. It's not responding to anything. Okay, so what we're going to want is basically our program needs to sort of parse out the packets and know what to look for. So we're going to kill that program for a second. And so this means we're going to have to figure out how to parse these bits. If we go back to this, you'll notice that what receive says is you get the MTU, which is basically just the packet size in your network. We're going to assume it's 1500. And you get +4 for a header that packet info is prepended. So this is what the difference between new and without packet info is. Specifically, in this case, there's a description somewhere here. The frame format that you get is you get 2 bytes of flags, 2 bytes of protocol, and then you get the raw frame. So if we look at the bytes that we received, this is going to be like flags this. Actually, we can probably do flags is actually, ooh. Probably want byte order here, but isn't there a... Didn't we recently get like read big endian or something in Rust? Oh, endian. Might not have landed. It might not only be nightly. This is going to be very handy regardless. BE? Yeah, from BE. So we're going to have a U16... from NE. U16 from NE bytes. Sorry, give me a second. I just need to make sure the chat doesn't turn off. There you go. Yeah, so this lets us basically parse out a U16 from bytes in native endedness. That's not what I want. I want LE. Because network... What is network? I can never remember. Big endian is network. Okay, great. So what we want is from BE bytes. So flags is going to be U16 from BE bytes. Is this on beta? Probably isn't, is it? Oh, yes. From BE bytes. And this is going to be buff 0, buff 1. And then what was the next thing? Where are we? Here. Proto. This is going to be 2 and 3. And this is going to be 4 and onwards. Ooh. Oh, right. We need to do some cleanup here. What's the bash term? The inline warnings is something that recently landed in Rust in the NeoVim language client. It's actually a little bit annoying because the default styling is pretty terrible. Capture term. Capture kill. Signal. Trap. That's what I want. Specifically, I want trap term. I basically want I wanted to terminate the program normally when you do a Control C. Can never remember what the syntax is for this. It's going to be kill PID. And we're going to kill this so it tears down this. And then we're going to run it again. Ooh. Invalid signal specification. That's interesting. Oh. That's right. Oh man, didn't tear it down? Well, that's obviously not working. Isn't there a way to like do nicer traps? I can never remember how this actually works. Is it sig term? I thought it was just kill PID. I thought that was all you needed. Oh, maybe this needs to be bashed, doesn't it? Yeah, okay. Great. Okay, so now run sh is gonna, when we kill it, it's also gonna kill the underlying program. And crucially, in theory, now we're gonna parse out flags and proto, and we're gonna print them here. Flags. Proto. Flags, proto. Okay, so proto 86DD. So I guess we're gonna have to figure out what these different protocols are. Where is the proto? That's unhelpful. I think it's from the IP frame. IP protocol numbers. What did we get? Proto's 86DD. Ether type. So 86DD is an IPv6 packet, right? And my guess is if we start doing pings, then now we're getting things that have protocol 0. This is 0800 and 0800 is IPv4. And so the first thing we're going to do is ignore any packet that is not an IPv4 packet. right? So that's going to just tidy up our stream a little. If proto not equal to this, continue. So at this point now, notice there's nothing printed when we first started because those packets went away. And indeed, if we now start pinging, those packets do in fact show up. Okay, so now we've parsed out the beginnings, and what now follows is an IPv4 header. And so what we're going to do is we basically have to encode this structure, the IPv4 header, in our Rust code somehow. I wonder if someone has already done this, just to save us the work. IPv4 network structs. Seems great. IPv4 header. Great. That seems fine. Let's use that. The reason I'm using a package for parsing IP is because it's not really what we're focusing on. So there's no reason for us to really redo that work. Ether parse is 08. And in main, here we're going to do, this is going to be ether parse IPv4 header slice from slice buff 4 to n bytes. And if this errors in some way, then we don't really care, right? That just means we're going to skip the packet. And so we're going to do a match on this. And if it's a packet, then we do whatever we want with the packet. And if it's an error, then we're just going to ignore that packet. Ignoring packet. Weird packet. And then here, what we're going to do is print out the packet instead of the buffer. And now let's see what that gives us. All right, let's see what now happens if we do some pinging. Okay, so now we're getting, oh, I guess the slice isn't really helpful, but at least it parsed it correctly, right? So that's pretty promising. So let's now have it, instead of just do that, let's try to actually print out some stuff. In particular, what we probably care about from the IP packet are things like the total length of the payload. So instead of all of the stuff we've done so far, we're going to do got IPv4 packet bytes of IPv4 packet payload, and that's going to be what, p.payload len. What else do we want? I think we're probably going to ignore all these other fields, but protocol we're going to care about. We're probably also going to care about source and destination. So we're going to do source is going to be p.sourceAddr. And destination is going to be destinationAddr. And what else do we have? Protocol. And notice that this protocol is different from the other protocol. So the protocol we get up here, these are for the Ethernet frame that we got. And so this is sort of set by the link level protocol. And that we're not really going to care about down here. Oops, what did I do? This, on the other hand, is the IP level protocol, which should be set to TCP. So in fact, let's print this out in a similar format to this, right? Just so here. So this is going to be the source, the destination, the protocol, so I guess this is going to be bytes of protocol this. This is going to be source, destination, proto, and that. So let's see what this gives us. Is there a way to debounce that Neovim plugin so it isn't checking out for every new character? I don't know. I really want that, and I haven't looked into it enough. It's a fairly new feature, but it's really annoying. You probably need time to live. I'm just going to assume that it's fine. Like, there are things that we should do that we're not going to do. Yeah, it's really, really distracting while typing. The MAC address we don't actually need because we're at the data link layer, sort of the IP layer. So we don't need anything like Ethernet frames. All we need to know is where to like respond to the packets. This is failing for some reason though. Why is it failing? Don't think it should be failing. Great. So now if we ping, what's it going to do? Great. So we got 1 byte of protocol 64. Okay, so time to look up the protocol. So 64. Ooh, that doesn't look right. Protocol. Oh, are we printing this in hex? We're not printing this in hex. How about we print it in hex instead? Also, let's get rid of these warnings. Don't need this, and don't need this. Protocol 0x40. So IP protocols. Oh, am I printing these in reverse order? Oh, you're right. Wow. Yes. That is the payload length. This is the protocol. Okay, better. So now if you ping protocol 1, and protocol 1 is indeed the ping protocol. Okay, great. Thanks for catching that. Yeah, so now at least we know that we're getting our IP packets, and we know that whatever is left is sort of TCP. So the question now is, what happens if I try to connect using a TCP client to whatever port? It's not important. So I'm going to try to do that. Okay, so it got 40 bytes of protocol 6. Protocol 6 is TCP. Okay, so we got a TCP packet of some kind, and we got 40 bytes of it. So this is where we really need to start getting into what are we going to do at this level. One thing we also have to decide is whether we are going to implement the packet parsing ourselves or whether we're not. So this is actually sort of up to you. There's a lot of stuff in TCP, and most of it is not about parsing, right? Like parsing the TCP header is not particularly, is not the core part of the TCP protocol, but it is a bunch of like bit fiddling. Ether, I think the ether parse thing also supports TCP headers. So we can use this to do the parsing for us. That way we don't have to spend a bunch of time doing the bit fiddling, but I'm also happy to do that. So would you prefer to see me start working on like the TCP protocol side, or do you want to also do the TCP header parsing? What would you prefer to see? To give you an idea, if I stop this for a second, if proto not equal to 0x06, Just while you're thinking, I'll write up the one that uses ether parts. Is there a header len here, I wonder? So this parsing is just the same as the IP parsing I did above. I guess. TCP to port this. And I guess that's going to be P dot. Is there a way for me to get the length from this, I wonder? Huh. That's interesting. I guess dot, it's going to be P dot slice dot len and P dot destination port. Let's see. Protocol, I think I'd prefer to not see parsing, just a protocol, parse, protocol, protocol, skip parsing. Parsing might be interesting, protocol, skip parsing. Okay, so it sounds like protocol then. Great, so we'll just do the protocol. So I've now done the parsing. This is why the parsing is nice to skip, basically because etherparse does the parsing for you. If you're curious about like low-level parsing, I would look at the source of etherparse. It's mostly just like reading out. So you have a byte string, right? And then you do things like this sort of U16 from B bytes, a U8 from B bytes. You just like read out the different fields according to what the specification says that the header formatting is. You get out the fields and then you sort of parse them in the appropriate way. And my guess is if you read the etherparse source code, that is all it does when you use this from slice business. Why is this stopped following? Very annoying. Let's see if this gets better. Okay. All right. So if I now run this, what happens? Oh, I need to type my password apparently. That's fine. All right, so now this is running. Eventually we're going to need all the fields of the TCP header. I just didn't particularly care about printing it right now. So let's now let's try to ping. You'll notice that nothing gets printed because we notice that it's not a TCP packet. And then if we try to send a TCP connection, you'll say we get 40 bytes of TCP to port 80, right? If I stop this and say 443 instead, it's going to say 40 bytes of TCP to port 443. Okay, so at this point, we are receiving TCP packets. And so now the question is, what do we do with them, right? So at this point, now we sort of know that there's something going on here. And so now we need to figure out what we're going to do sort of in order to implement the protocol. The thing to keep in mind is that in TCP, a connection is, or well, everywhere, a connection is basically a quad of source IP, source port, destination IP, and destination port. Oh man, these warnings are so annoying. What's the thing for turning them on again? Sorry, I just need to Didn't I fix this at some point? Thought I did. Apparently not. All right. Well, NeoVim language client. I could write it as comments. I just don't want this feature to be on like ever. It's far too annoying the way it currently is. Virtual text. This. How do I turn this off? This. Excellent. It's gone. Beautiful. I can still put it in a comment though. So we basically want this quad like this. This identifies a single connection. And anytime you run sort of the TCP protocol, you basically want to run it on this quad. Like all the state is associated with that quad. And so what we sort of need is almost like a map from this quad to the state for that connection, right? So we're going to end up constructing something like TCP state. And that's going to contain a bunch of fields. And then we're going to have something like connections, which is going to be a hash map. Well, actually, let's make it default. This is going to be a hash map from a quad to a TCP state. And a quad is going to be a source IP. I guess actually we could. I'm not going to. I don't think you should generally use this for anything. No, this is building more because it's interesting, not because we're going to use it for anything. So the source is going to be a. I guess this at this point, we need to figure out what this return type is for the. It's a TCP. It's a what? Where's the source adder? IPv4 adder, which comes from standard net. So we're gonna use standard net IPv4 adder. IPv4 adder and a U16, right? So this is source IP and port, and destination IP and port. This, of course, we're going to derive like all the things for. So the hash, eq, and partial eq. And probably also debug. And probably also clone and copy. Right? So we're going to keep this sort of connection state, and that's going to be from one of these to whatever we end up putting in the TCP state. And just to make our lives easier, we're probably going to do a mod TCP. tcp.rs, and that's going to have this. So this is going to be a TCP state. And so the question is, what do we do when we get a TCP packet? Well, in all likelihood, what we're going to do is we're going to do connections.entry quad, right? Which is going to be, the source is going to be the source address and the P source port. And the destination is going to be the destination address and the destination port. And the question is, what do we do if there is no connection? Well, we probably want or default. Like there's going to be some, default state that every connection starts up in. And then so the .entry API is really nice because what it will do is basically, if there's already something with that quad, it's going to give us a reference to that thing, to the corresponding state. And if not, it's going to create one for us and then give us a reference to that. So what we end up with after this or default is basically is basically always what we end up with is a mutable reference to a state. And so at this point, we're going to say something like on packet, and we're going to give it the P, and we're going to give it, actually, that's a good question. Why is there no way for me on this to get out